Okay, part deux. Part deux. I'm going to find the exact area of each sector. So today we learned that the area of a sector of a circle is equal to x over 360 times pi r squared times the area. And the sector is this section here that's shaded that we're trying to find the area for. It could have been this section, but we're asked to find this sector. And it's bounded by a central angle and an intercepted arc. So it's a portion of the circle, but it comes from the center of the circle here. Okay, so the area is equal to this. And I'll substitute in the measure of this arc that bounds in this sector is 120. So 120 over 360, that's the measure of that arc. And then the radius of the sector and of the circle is 6. So 120 over 360 times pi times 6 squared. Now I can simplify this by squaring 6. Zoom in a little more. And my area here, I'm trying to find the exact area, so I'm going to need to do some canceling because pi is going to remain pi. I can't just plug it into my calculator. So 120 over 360, that actually reduces to 1/3. And we have pi times 36. 120 goes into 120 once, 120 goes into 360 3 times. And then I can cancel here. 3 goes into 3 once, and 3 goes into 36 12. So the final answer here is 12 pi. That is the area, the exact area of that sector. The whole area, just to point out, the whole area is pi r squared. That's the whole area. And the whole area is equal to pi times 36, right? 6 squared. So that's the whole area. And if you'll notice that the arc is 1/3 of the whole circle, and this area of the sector is 1/3 of the whole area. We're looking at partial parts of a whole area. Just so I point that out. But the answer here for the sector is 12 pi. Number 10. The area of this sector is equal to the measure of the arc over 360 times the whole area. And if this measure here is 90, then this arc is 90. Central angles are equal to their arc. And if this arc is 90, then this whole remainder arc is 360 minus 90. So 360 minus 90 is 270. So this arc right here is 270, and that's what we're going to use in our formula. So x equals the whole arc here. Look, it's a large portion of the circle. So 270 over 360 is quite a big portion of the circle, times the whole area of pi, radius is 6, so let's just make that 36, r squared. Now this can be simplified. We want the exact. We're going to leave pi as pi. 36 goes into 36 once, and 360 10. So I get 270 over 10 pi. I can cancel out the zeros, and I get 27 over 1, which is just 27 pi. So the area of the sector is 27 pi. The area of the whole circle, just to look at here, is pi r squared. So that's 36 pi. And you can see that the area of the whole circle is 36, and this is a good portion of it. Might be 3/4 of it. 3/4 of it. Okay, 11. The area of a sector is 24 pi. So we're already given the area of the sector. And we're also given the area of the whole circle. So find the measure of the arc. And when we're not just looking for the area of the sector, when we're actually given the area of the sector, I like to use a proportion. So the area of the sector is to the area of the whole circle as x is to 360. So in other words, the area of the sector over pi r squared is equal to x over 360. So there's the proportion. So what do we know? We know the area of the sector is 24 pi. And we know that the area of the circle is pi r squared, and we're told it's 60 pi. This is the area of the circle. So 24 pi over 360 pi equals x over 360. We're looking for the measure of the arc over the measure of the whole circle in degrees. Now this can be canceled a little bit before we cross multiply to solve for x. So I'm going to cancel off the pi's. And I can divide 24 by 6, that would be 4. And 60 by 6 is 10. I probably could have gone further, but that's okay. So 4 over 10 equals x over 360. And let's cross multiply. 10x equals 4 times 360 is 0, 4, 1, 4, 4, 0. Divide both sides by 10, and x equals 144. So the measure of the arc is 144 degrees. Number 12. Find the perimeter of the sector in number 9. So we're going to find the perimeter of the sector, which means that, and we want to find, if it doesn't say, let's just go ahead and find the exact. We have to find the arc length, and then we can add it to this radius here and this radius here. So we're going to find the distance around this whole sector. Now arc length is very similar to the area of a circle. Remember, it's a portion of the circle times the circumference now. So let's find the arc length. The arc length is 120 over 360 times 2 times pi times 6. Simplifying this will give, this can be simplified to 1/3 times 2 pi 6. Simplifying further, 3 and this becomes 1, this becomes 2. I get 4 pi. So the arc length is 4 pi. Hopefully you saw all my quick simplifications there. Now 4 pi is the measure of the arc length. So let's add that to 6, which is this side of the sector, plus 6, which is this side of the sector. So we get 12 plus 4 times pi. Number 13. Let's find the area of these special triangles. And I mentioned today that these are pretty key figures in trig and other math classes. We have an isosceles triangle here, and we're asked to find the area of it. So we'll have to drop a height down. And if you drop a height down from the vertex angle of an isosceles triangle, then it not only bisects this side and this side, but it also bisects the angle. So this whole angle was 120, then this angle right here is 60. So what we have is a 30, 60, 90 triangle for half of this isosceles. This is 60, this is 90, this is 30. So we can find the length of the height. If the hypotenuse is 8, then the short side, this is the short leg, it's opposite the 30-degree angle, is 4. This is the long leg of a 30, 60, 90. So the long leg is 4 rad 3. The area of a triangle is 1/2 base times the height. Well, the height is 4 because it's half of the hypotenuse. And the base is 4 rad 3 plus 4 rad 3, which is 8 rad 3. So we have 1/2 times 4 times 8 rad 3 times 4. 1/2 times 8 is 4, so that's 4 rad 3 times 4, and that's 16 rad 3. Notice I'm multiplying everything on the outside of the radical. The radical stays inside, stays the same. So the area for this triangle is 16 rad 3. If you try to use the Pythagorean, it doesn't work here because we weren't given the base, but we were given information to make it a 30, 60, 90. But other times you might use the Pythagorean for this. Now, number 14. Is an equilateral triangle. And similar to the isosceles triangle, if we want to find the area, which is 1/2 base times the height, we'll draw a height down from the vertex to the opposite side here, and that's at 90 degrees. It's an altitude we just drew. But this altitude not only bisects this angle like it did over here, but it also bisects this side. So this side and this side are now congruent, this little section and this little section. Well, it's an equilateral triangle, so we know that this is 10, and this is 10, and this whole thing is 10. We just need to find the height. Well, the height, if we notice, this is an equilateral triangle. Every angle is 60 degrees in an equilateral. So this is 60, this is bisected 60, so it's 30. So this is a 30, 60, 90 triangle. When you divide the equilateral triangle in half with an altitude, then you do get two 30, 60, 90 degree triangles. This is 10, this is 10, this is 10. The height, well, here's the hypotenuse. This is the long leg, so we'll need to find the short leg first. Always find the short leg first in 30, 60, 90s. So if this is 10, then this segment is 5, and the height is equal to 5 rad 3. The area is equal to 1/2, the base is 10, and the height is 10 divided by 2 times rad 3, 5 rad 3. And we get 5 times 5 rad 3. I'm just multiplying 1/2 times 10. 1/2 of 10 is, oops, sorry about that. So its area is 1/2 times the base times the height of 5 rad 3. And then 5 times 5, let's see, so 1/2 times 10 is 5. Then I'll multiply also, multiplying everything that's on the outside, 25 rad 3. And there's the area of the equilateral triangle exact, using 30, 60, 90s again. So have those formulas memorized, those 30, 60, 90, and the areas of these shapes need to get put into your memory banks. I'll see you tomorrow. Have a great evening.